Actually, I don't know where this idea even came from and how it could have arisen in someone's mind, but someone, somewhere, perhaps on some forum, maybe in some sort of scientific discussion, said that if you melt all the metals together, at once you would get an alloy with incredible properties, possessing characteristics that accordingly have not yet existed on our planet. Maybe it would be something like the material for Captain America's shield. Maybe it would be some kind of super duper metal that would allow, like, the TV-1000 does to pass through walls or something like that. Let's start with the simplest. A metal alloy is quite a standard system that consists of at least two components. This is a metallic component and possibly a non-metallic component. Many of you think that a metal alloy necessarily involves the interaction of some metal with another metal, some kind of symbiosis like that. To some extent, this is appropriate and correct, but in principle, you are mistaken. And why are you mistaken? Because, for example, let's take the most well-known, the most common alloy, which is called steel. And this alloy consists of iron and carbon. As you understand, carbon is not a metal. Nevertheless, there are, of course, metal-metal alloys. And this is also a common system. And now let's do something mischievous. Let's take some other material, consisting of another chemical element, and add it to the molten metal. What should happen? Well, here again, strangely enough, it's appropriate. The very analogy that we often use when we imagine some balls of one element and balls of another element. The balls represent atoms and such. An analogy is appropriate in this case. But always be careful with analogies, because if it is appropriate here, it may not be appropriate in some other cases. For example, in the world of quantum physics, such an analogy does not work right away. It is incorrect. But here we use it. And so we imagine that we had a pure metallic component, a pure element that represented some metal, let's say in a molten state. It consisted of atoms of one element, of balls of one type, one kind, one color, however you want to imagine it. And now we take other balls and pour them into the same bucket where those balls were. Let's say we had white balls and green balls. The white balls, let's say, were aluminum, and the green balls, let's say, were copper. And so when we poured all of this in there, we ended up with, what did we end up with? It seems like we got an alloy, but don't rush to answer. In fact, it's much more interesting and complex. Strange as it may seem, the balls possess certain properties, specific characteristics, certain parameters, and particular activity. That is why, when we encounter two chemical elements in a material, these spheres, visualizing atoms, cannot remain indifferent. They will always try to engage in some kind of reaction. And there can be many reactions, they can be different, and the processes can be completely varied. This depends on the properties that the atoms in the melts have. And the atoms themselves can differ in almost anything. The number of outer electrons, the amount of energy, the amount of, well, whatever else. They can differ in mass. They can differ in size, atomic radius, and there are quite a few parameters here that we can list. But it's important to understand that for these little balls in our common pot, which we are trying to mix, to start interacting in some way, there needs to be a match. Imagine a Lego set, and this set has pieces that have connectors, and there are pieces that have, let's say, a mechanism for securing these connectors. The pieces can fit together or they may not fit together. The same situation applies to our little balls. The balls can connect with each other, or they might not connect at all. And when we are trying to obtain a metal alloy, we need the balls to connect with each other. And when will such a connection occur? Here, you need to go through this much literature, or perhaps even this much literature, to describe all of these. But I think, in general terms, we can bring up the possibility of forming a chemical compound, the possibility of forming a mechanical mixture, and the possibility of stable coexistence within a single substance. There are materials, there are chemical elements that are fundamentally immiscible. They will never coexist with each other. And every time we mix different elements within one cocktail, we must proceed from the fact that the elements should interact with each other. We must proceed from the fact that any metal alloy is a complex system of components, specifically designed to coexist together, and possess special adjustable properties. This means that any alloy is developed in millions of ways. The simplest ones, I think you can guess, is the method of trial and error, where you mix, observe. It's the method of working through theoretical data. It's the method of applying some unconventional techniques. For example, I once had a topic called non-mixing components, and various approaches were used there to mix these non-mixing components with each other. And now it's time to say that if we take all the chemical elements that we have, that we currently know of, that we can take and that exist under normal conditions, it won't allow us to combine them into an alloy. Why won't it allow us? Because all elements have different properties. These properties are numerous. Listing them all now would take a very long time. But remember the most important thing, everything we discussed at the beginning of the video. All the elements that are in a certain metallic material, in a metallic alloy, must come together with each other. Within the alloy, there should be either a solid solution, a mechanical mixture, or some other characteristic states. And what is, for example, a solid solution? It's when an atom of a foreign leading element penetrates the main crystal lattice, which we have talked about for so long, and which you surely already know about, even without me. And, for example, it displaces an element that is not exactly superfluous, but does not have sufficient bonding with its neighbors, or replaces it. So, when we take all these elements together, when some elements are capable of interacting with each other, and some are not, we end up with, as you understand, something unclear. And this something unclear is unlikely to have properties sufficient for a metallic alloy. And never mind the properties. What is important is that we imagine an alloy as a kind of homogeneous system. So, when we try to fuse all the elements of the periodic table, we won't get anything, but rather an unclear mishmash. Some chemical elements will be able to enter, for example, into a chemical reaction, forming stable compounds. Some chemical elements will be able to displace other elements. Some elements will be able to form a stable mixture. But those will not be able to interact with each other in the way we want to see. Many elements are fundamentally incompatible with each other. For example, if you take up atoms with significantly different atomic radii, you simply cannot fit them inside, for instance, a solid solution. Imagine that you have a crystalline structure that consists of atoms and looks like some kind of incomprehensible cage. And then you take an atom whose atomic radius is significantly larger than the existing distance in this cage, and you try to fit it in there. We simply won't be able to create a solid solution for incorporation. The elements will simply remain separate, one element and another element. Therefore, no matter how carefully scientists try to select interactions and correspondences, when there are so many elements, it won't work. Moreover, another interesting thing will manifest. Some elements will start to actively interact, will begin to engage in suici, let's say beneficial relationships, strange as it may sound. And this will allow them to somehow form a more or less stable state, a more or less stable phase. But when this stable phase encounters something else that has entered the same melt, and there is a lot of something else, we will again end up with something unclear. Therefore, no matter how carefully we try to select the correspondence of the ratio, nothing will work.